So basically, I have 3-4 cases over here. So we will try to cover as many as possible. So here, as sir has mentioned, our cases are divided into two parts. One is which is based on the VOF. Okay, the ones which are based on VOF are the VOF bubble, dam break. Okay, VOF bubble and dam break are based on the what you can say VOF approach, and then fluidized bed and bubble column are based on the two fluid model, that is the Eulerian-Eulerian model. So these are the different cases. Okay, so let us move on and let us look at the first one, that is VOF bubble. So again, what are the case structure is similar, right? You have zero, constant, and system folder. Now in zero folder, we have something called as alpha dot water, and then PRGH and U. So in this case, right, we are solving for the phase fraction. So alpha means the phase fraction. That means what is the volume of the phase to the total volume of the cell volume. So that is our phase fraction. So we have one file in which we are specifying what is the boundary condition for this phase fraction at the different patches. So what are the different patches? So first of all, let me show you the what you can say how the case setup looks like. So I will open the case that is run already. Yeah. So you see, this is our setup. Okay. So what we have is we have a so in the block mesh, we have three walls. That means the sides and the bottom is of type wall and the top is of type atmosphere. So this is our case setup. Now we have to look at the boundary conditions for this. So in alpha dot water, for all the walls, that is the side and the bottom, we have given the boundary condition of zero gradient. This means that the phase fraction doesn't change near the wall. Between the cell and the wall, it is same. Now, this also means that we are not modeling for any contact angle. Okay, if we give any contact angle, then zero gradient basically means that the contact angle is 90 degrees. So the interface is at right angles. We can give a contact angle also in this place. That is also possible if we want to simulate that, if that is what we need. Then for the atmosphere, we are giving an inlet outlet type of a condition. And we are saying that the phase fraction, that means we are saying that we are allowing for reverse flow, and if there is reverse flow, then alpha dot water will be zero. Okay, that is what we are trying to say over here. Then the next is PRGH. Now in PRGH, for all the walls, we are giving a fixed flux pressure boundary condition, right? And for the atmosphere, we are giving a total pressure. This is generally used, when we want to simulate, say that like the outlet is open to the atmosphere. So then we simulate that by considering the total pressure. And default faces are just front and back, so they are empty because we are doing a 2D simulation over here. So that is a PRGH folder. And velocity, if you see, all the walls are of type no slip. So sides and bottom are no slip, and the top is pressure inlet outlet velocity. Okay, this is more like a zero gradient type of a boundary condition. Okay, but again accounts for reverse flow. So this is zero. In constant is where we are going to specify the properties. So if we are adding turbulence, then it will be mentioned over here. But this is a laminar type of a simulation, so we have kept the turbulence to be off. Now in the transport properties, here is where we need to specify the phases. Okay, so we have only two phases, that is water and air. And for each phase, we will specify their transport properties separately. So for water, the transport model is Newtonian, and we are specifying the viscosity and the density values. Okay, for water. Similarly, for air, the transport model is Newtonian, and we are specifying the viscosity and the density. Now, sigma is the surface tension. So surface tension between the air and water. So that is also given. So these are the properties that are needed. Okay. So this is in the zero constant folder. Now in the system, we have gone over the block mesh utility. Then Decompose power dict, see, it is used if we now the mesh size that we have is slightly coarser, right? Because this is only for demonstration. If you have a very fine mesh, you want to refine the bubbles, and get a very sharp interface, then the mesh also has to be equally fine. Or you can go for adaptive mesh refinement that we will define show in the next demonstration. But still the mesh will be slightly finer than this. So then we need to simulate this as not as a single case, but in parallel. So that time we need to go for decomposing the domain. And in this case, if you see, we have used the Scotch method, which will do it automatically. So we don't need to specify any parameters like what will be the decomposition in the X, Y, Z direction. That we don't need to specify in this case. Okay. Now, so if you see, generally in open form, when you are initializing temperature, pressure, or anything, we just initialize it in this zero folder, right? Say if I open alpha.water, if you see the internal field, whatever value you specify, the complete domain will be initialized by that value. Okay, so that is called as a uniform initialization in one time. But whenever you want to do a non-uniform type of an initialization, then we can't do it from here. So we have to make use of the set fields utility. So that is what this, what you can say, set fields dict is for. So if I open the set fields dict, so again, you see, if you have followed the topo set tutorial, this is kind of similar to the similar to it. So what I'm saying, by default, the value for all the fields alpha.water is 1. That means I'm saying the complete domain is water for the time being. Okay, alpha.water. Now what we are saying is, for when we have to select cylinder, because remember this is in 2D, so the bubble in 2D will look like a cylinder. Okay, that's why what we are doing is we are using the cylinder to cell function to select all the cells within that. So if this is open, so see, we want to select all the cells that lie within this domain, within this blue box. Yeah. So we are selecting that by specifying the center. You see, we are specifying 2 points, right? P1 and P2. So these are the centers of the two circular faces of the cylinder. That means this center and the center of the back face. Okay, so those are the 2 points, and we are specifying the radius. So just by specifying these, what you can say, 2 points and the radius, we are able to select all the cells that lie within this. So if I just do this, and if I do surface with edges, you will see that all the cells that lie within that, right, are selected. Okay, and those cells are initialized with water. So that is done. So first is the cylinder to cell utility. So this will select all the cells that lie within this domain. Now in all the cells, we are saying that alpha.water is 0. So if alpha.water is 0, that means that phase is completely air. So that's why if you see it becomes blue, that means that is air bubble. Similarly, we have initialized this. We also need to initialize the top section, right, with air, because we are not what you can say simulating. We are not allowing a what you can say interface from where it can leave. So we have extended the interface, and we are simulating that at the top there is air. So we are simulating the interface between water and air as well. Okay. So the top section also needs to be initialized. So we have the box to cell utility to select the cells in the top. So how do we do that? Again, you see, we need to specify 2 points. Okay, what will be those 2 points? So if I were to say that 1 point will be this corner, right, from where the blue one begins, and one will be the corner point at the top. So diagonally, how I had shown in the diagram. So by specifying those 2 points, we can select all the cells within that box, and for them again alpha.water is 0. So this is to initialize the fields non-uniformly. So set fields utility is used for that. So now, see, we are using the solver that we are using is interform, and we are again using adjustable time step with maximum Courant number and maximum alpha Courant number. That is this is the Courant number for the flow, and this is the Courant number for the interface. That is, maximum values are limited to 1. Okay. So with this setting, let us now try to simulate this and see how this works. So I think I've opened it in the terminal. Yeah. So first let me source my open form. Then I need to do block mesh. So once I do block mesh, if you see, my domain is ready, right? And if I do alpha dot water, it is completely water. Okay. So nothing is initialized because this is the right till now we have not run the set fields utility, right? So it is taking the values from the boundary conditions file. In that we have initialized the complete domain to be of water. So that's why we are getting this. Okay. Now after this, let me run the set fields utility. So as soon as I run set fields utility, right, it is selecting those cells and initializing it to be, with water. So now if I run paraform command, and if I click apply, so you see those fields are initialized with air. So that is what the set fields utility does. Now we need to solve this. So because it is a simple case, I'm not decomposing it. We can just solve by running the command interform. Okay. And it solves pretty quickly. So we just have to run for 0.3 seconds. So another few seconds. And then we can look at the results. So see, if it is a coarse mesh, it runs very fast even on the single core. We don't need to decompose. Yeah. So we have finished running. So now let us look at the results. Yeah. Now, if I click play, you see the bubble rising, the oscillating, deforming, and going up. Okay. Now, if you refine the mesh, then you will see much more clearer behavior with this. Okay. And you see the top interface also moving when the bubble kind of hits that. Okay. That is also moving. So this is something that we have simulated. Now, here we see that the interface is being tracked. Okay. This is VOF. Now, if you look at this, our mesh is very fine. Okay. What if you want to use something called like adaptive mesh refinement? So now for that, let us go ahead and look for the dam break case. Okay. So in this, I am not taking the standard dam break case. I am taking the case with dam break with obstacle. So this is already available in your tutorials. You can go. One more thing that I kind of forgot, but I will go to it is if you look at this VOF bubble, right? Hmm? If you look at this, the file name alpha.water was named as alpha.water.org, right? Means for original file. Why we do that? Okay, because if you don't do this, now if I open this alpha.water file, see what happens. This is after the simulation has ran. Okay, see, it is not responding. Why? Because the file size has become too large. Why is this? Because when we run the set fields utility, this file, the alpha.water file gets overwritten and all the values of the phase fraction get written in this file and this boundary condition moves down. So later on when you want to modify any changes, then this will not open and it will create problems for you. So the best way to do it is your alpha.water file, you should name it as alpha.water.org, right? So this file open form reads, but when it is when after you run the set fields utility, it will not overwrite onto this file, but it will create another file alpha.water. So by this way, you will not mess up your boundary conditions files in case you want to make any changes. So this is why you need to rename it as alpha.water.org, means like the original file. So that is why all these cases you will have the alpha.water file written as alpha.water.org. Yeah, so now I wanted to go to what you can say dambreak.obstacle this I don't know if you all have seen the dam break case. Maybe I show you the dam break case first. I'll directly go to that one folder. Let me run this. Okay. Again over here, generally, you see the setup. I wanted to show you the setup. Again, yeah. So this is our domain. So if you see, so our domain is like a room which has an obstacle. So if I slice it in my X normal, or best way is I will reduce the opacity. I will reduce the opacity. Yeah. So now you will be able to see that we have an obstacle in the center, and then we have a column of water on the side over here. I guess this way. Yeah, a column of water on the side. Now, what is this dam rig? Basically, what we are doing is we are keeping on column of water, and it is imagined that it is held in by some sort of like an elastic, what you can say, membrane. And as soon as that membrane breaks, what will happen? That whole water will start to fall down. Now, using interform, we can track that complete interface, right? And we can see how that motion happens. So this is the idea. Okay, so this is how we need to set up this case. Yeah. Let me go to the actual case and show you the case files. So generally, again, alpha dot water. See, this is what I was talking about. See, alpha dot water file, because once we run the set fields utility, it gets rewritten, right? And all our boundary conditions get pushed down. And sometimes it does not open properly. So it is always best to name your file as alpha.water.oring. This is a case that I have already run. Let me go to the. If you see my alpha.water, so here for the walls, again, zero gradient. For the obstacle also we have zero gradient, and at the atmosphere, similarly, inlet outlet is there. Zero gradient means contact angle is 90 degrees. Okay, remember that. And then these are some turbulent properties, PRGH and the U file. U file again, it will be for the walls, it will be zero gradient, and for the atmosphere, it will be inlet outlet. Now in constant, we have one more additional file over here, that is dynamic mesh dict. Why do we need this? Because if you see the bubble rise, we had a uniform mesh throughout. Okay, but this is additional utility, right? With which we can refine the mesh near the interface. So I will run this, and then maybe I should show you this, and then maybe you will be able to appreciate this more. This is the run case, right? So let me make a slice over here. So this will give me a good slice. Yes, I'm hiding this. Okay, yeah. So if I go to the, so if I just do this, okay, I think I should keep the main box on so that this is seen. Right? Yeah. So you see there is a column of water, right? And as we hit, that column of water is breaking, and that fluid is spreading, and it is moving around the obstacle. So it will go around the obstacle as well. So if we want to capture this, we want to capture that interface properly, right? So in this case, what we have done is, let me go ahead and hide this. Yeah. And then instead of, let me go to alpha.water. Yes. So if you look at this now, okay. So we have alpha.water over here, correct? So that means we have the initial water column. This is not actually at the initial time. This is at the first time that we are writing. So if you see, near the interface, the mesh is resolved, right? And at outside the interface, the mesh is quite coarse. Okay, this is what we are talking about, adaptive mesh refinement. Okay, so let's see what happens. As soon as I play it, right, it is moving. See, if I do it one by one, okay, that domain is moving, and as that domain is moving, the mesh is adapting to it, right? The mesh near the interface is always resolved. Okay, and wherever the interface was previously there, then that mesh gets changed again. So this is what. So if you see, the interface keeps getting resolved. Okay, so this is the advantage, that we can have a coarser mesh in the domain where we don't we don't need such a lot of computational effort. The more computational effort is needed at the interface. So we resolve the mesh only in that region. So that is what is needed. So this can be done by using the adaptive mesh utility, right? So for that, what we need to do is we need to use this dynamic mesh dict in the constant folder. And in that, we need to so this is a refinement interval. That means how often you want to refine. That you want to refine every time step, right? And in the field, I want to refine based on the alpha dot water value. That means if my alpha dot water value is between 0.001 and between 0.99, let me refine that. This is because this will capture the interface, right? Everywhere else, either it will be completely 0 or completely 1. Within this, we are capturing the interface. So there it will resolve. And for any level that is less than 10, it will says you start to unresolve that. That means except the interface, everywhere else you start to unrefine it. Otherwise, it will remain refined. That is what. Then the buffer layers and maximum refinement is what you can see. Evan already discussed, right? Refinement level of 2. What does refinement level of 2 mean? 4 mean? Okay, that. And again, maximum cells. So sometimes what happens is if we don't, what you can say, it may keep refining, right? So we need to put some stopping criteria. Okay, if the cell limit exceeds, or in this case 2 lakh, then stop the refinement. That is what we are doing. Then correct fluxes are needed, because at the interface, when you're breaking the volume into another set, what happens is the fluxes are calculated for those each cells. So they then get recalculated for those mesh that is again done. So that recalculation, if you want it done, then you specify. Otherwise, you can leave it as none. Okay, and then if you want to write the refinement level, then this has to be true. So this is just the basic thing that needs to be added, and with this utility added, we will be able to resolve the interface. So this is something called, that is very good in OpenFOAM, that you can refine the interface only near the, you can refine the mesh only near the interface. So for that, remember, you need to change only one thing, that you need to include the dynamic mesh dict in your simulation. Nothing else. All the what you can say code remains same. Block mesh, set fields, and then interFOAM. So the working is pretty same. So the other thing that I wanted to show you was Dambrick 4-phase. So this is again I'll directly show the result only. This is the same case as Dambrick. Only thing why I'm showing this is because, okay, let me open this in view and then I will show you. Yes. What is starting? Because of the data, it is taking some time to load it. Maybe let me try again. Okay. So here, so here you see there are 4 phases, alpha dot air. So all the values in red is air. Okay. Then alpha dot mercury. So at the bottom we have mercury. Then we have an oil. Okay. Then we have water. So this complete domain over here, right, is filled with water, oil, mercury, and then the remaining is air. So what will happen once we simulate and once this interface breaks? Because now we have fluids with different densities, we expect that the heaviest fluid should be at the bottom, the lightest fluid should be at the top. Okay. So in this case, this is what we are simulating. Actually, I will show you the result and then let us see. So if you see what happens to water. Okay. So let me have all the alphas. Okay. So here the different alphas are there. Okay. If I click, so remember the light blue was oil, right? The creamish one was mercury. Hmm. Then the blue one is water and the red one is air. So you see oil is going on top of water, water is going on top of mercury, and mercury being the heaviest is sinking at the bottom. So this is how we can simulate all the different phases mixing. Let me go to the last time step and you see what happens in the end. In the end, we have mercury at the bottom, then water, then oil, and then the last one is air. So how do we set up such a case, right? So for such a case, if you see, for each phase, there is one, what you can say, phase fraction, right? And we need to specify boundary condition for each phases. Yeah. So here at the atmosphere, inlet outlet, that means allowing the reverse flow. Okay. Just let me open the ORIC file. Yeah, this is better. Okay. So here, this is what I was talking about, right? So here you can either have what you can say type zero gradient. The zero gradient considers that the contact angle is set to 90, or you can specify the contact angle separately, like how it is done over here, right? Using the contact angle feature. Now, so it remains same. The other thing is properties will be in constant. Yeah. So in motion transport, we are not including transport properties. See phases. So if you see now, 4 phases are there, and all of them are separately defined, like water, oil, mercury, and the last phase is air. And then surface tension for each of them is given separately. So surface tension will be for a combination, like surface tension between air and water, air and oil. Here, I don't know, for simplicity, all have been given as the same value. This is the by default the case that is available in the tutorial that I'm showing to you. Okay. So this is something that you can look at and maybe modify to see how things change. Okay. The other, I have only 15 minutes with me, but let me quickly go because the other two are actually very important cases. Those are fluidized bed and bubble column. So let me go to first bubble column. Okay. So now bubble column case is the case of a two fluid model in which sir was saying that we are not interested in like these the cases that I showed you, in that we are tracking the interface between the particles. There is a separation between the phases, right? But in this case, Eulerian-Eulerian framework does not work like that, right? So how is that set up? So first let us look at the result, and then I will show you the case setup. So this case is pretty simple. So I have alpha dot air and alpha dot water. So let me show alpha dot air. So if you see at the top we have air, then we have water. The blue is water. Now as soon as I click, we see that what is happening. From the bottom, air is coming, right? And it is mixing with the water, and we have a dispersed phase. So we are seeing that both these phases are coexisting over here, right? And then we see some mixing that is happening. So with this, you can simulate that if you have a big container and if you're adding air from the bottom, how that air will move within the container, whether it will mix and go to all the regions or it will accumulate in one region, something like that. If you want to simulate, that can be done. So this is just a template case for that, right? Now, if you want to simulate a case something like this, then what are the properties that we need to set? That is something important. So let us go those files. So Let me go to the template case, become easier. Yeah. So in 0, again, we have alpha.air, alpha.water, these files. These files are similar, right? You will have boundary conditions. Only thing is, because we are giving some sort of like a sparging, we are saying that at the inlet, the value of the phase fraction is 0.5. That means 50%, right? And at the outlet, we are giving inlet outlet, allowing for reverse flow. Okay. And if there is reverse flow, then alpha.air is 1. That means we are allowing reverse flow of air. At the walls, zero gradient. Again, no contact angle between the walls is simulated. Then for the water, same. At the inlet, the phase fraction of water is 0.5. At the outlet, it is inlet outlet, but we are not allowing reverse flow of water. Okay. For the walls, we are giving zero gradient again. Now, P will be calculated. PRGH, we are giving fixed flux pressure, and PRGH total pressure for the outlet. Okay, and the walls again fixed flux pressure. Now this fixed flux pressure basically adjusts the pressure gradient to take into account also the body forces at that patch. So this is kind of similar to zero gradient, but takes into account the effect of body forces. That is what this does. Then temperature files, if we are simulating heat transfer, then we need to add the temperature boundary conditions as well. And the velocity files. So if you see, we are giving a fixed value at the of velocity at the inlet, and that is corresponding to the internal value. So here, because it is vertically aligned, the flow is along the positive y direction. So our velocity is 0.1 in the positive y direction. At the outlet, we are having a pressure inlet outlet velocity type of a boundary condition, right? And at the walls, it is no slip. So we are giving a fixed value of 0. Similarly, for the water, again, we have the same water. So we are not injecting water, right? So water, the velocity will be 0 throughout. Only air is coming in. So that's why the velocity will be only for air. But let me go to constant. The main So the main file is the constant file. So G will give you the acceleration due to gravity that you need to specify. Again, this will be in the negative y direction. Then we will the momentum transport between air and water. These are the transport properties. Okay. If we are simulating for turbulence, then we need to specify. Here in this case, we have set it to laminar for both. Then thermophysical properties. This is something similar to what we discussed in CHT. So this is used to specify the properties and how the properties are calculated based on change in pressure and temperature. Okay, so this is the class that does that. Okay, now what is the most important file over here is this phase properties. This is something that we need to look at in detail. So here we see that there are two phases, air and water. Okay, so air is our dispersed phase and water is our continuous phase. Okay. Now, for air, what type of model are we using? We are using the pure phase, and the diameter model is isothermal. Okay. So now, what is this diameter model? So if you remember, Professor Naren said something that we need to the coupling between the phases is done by the drag force. Okay, and drag force is calculated by the relative velocity, the density, and the area of the what you can say area of the interface that is there. Okay, so but here, because all the phases coexist, then how do we calculate that area? So to calculate that area, we consider that these phases are made up of what you can say particles of small diameter. Okay, so that's why we need to specify that diameter. So we can either specify, as in the case of water, a constant diameter. That means water will be considered made of particles of constant diameter, particles, bubbles, whatever you want to call them, of constant size, and that will not change throughout the domain. So, but air is considered to be based on the isothermal model. That means the diameter changes only with pressure. So, as the bubble moves from higher pressure to lower pressure, its size will change. So that's why that is how this isothermal model works. Okay, so your size is related to the pressure in the medium. So if the pressure decreases, the size will be more. Pressure is high, the size will be less. So that is what is this isothermal model. And in constant diameter model, the size is fixed. Okay, and this size is what is used for the calculation of the drag. Okay, So based on this diameter, the interface area comes into picture, and uh, based on this, the drags are calculated. Now there is something called as blending. So if you see, um, this is a case of what you can say bubble column. In this, in some regions, right, where the air is kind of fully mixing with the water, what may happen is the phase fraction of air becomes too high and the phase fraction of water becomes less. In that case, that may become a system in which water becomes the dispersed phase in air, or in some cases, water quantity is more, air quantity is less, and it may become that air is the dispersed phase in water. So both of these can be there. Now, what this blending does is, whenever you are applying a drag model, the drag will always be based on whether it is air is flowing in water, water is flowing in air, or both of those mediums kind of coexist. So that is decided based on this blending factor. So here we need to specify what is the minimum fully continuous alpha phase and minimum partly continuous alpha phase. That means for any phase fraction less than 0.1, it will be considered as a dispersed phase, and for phase fraction more than 0.7, it will be considered as a continuous phase. So this kind of brings that limit, and based on this, the blending is done. So it is decided whether one phase is dispersed in the other, and then the drag forces are what you can say set accordingly. So here you see the default blending. If we don't specify a separate blending, then this default blending will be used for all the models. But for any specific model you want to change that, then you need to write the name of the model and then specify a blending for that. So here they have said a default blending of 0.7 and 0.3, but for drag they change it to 0.7 and 0.5. Okay. Now if you see, the surface tension value between air and water has been given. Interface compression, this is there because this model allows for sharpening the interface, but then that is of no use for us in this bubble column. Okay. Then the aspect ratio. Aspect ratio generally says what is the shape of the bubble, right? Whether it is spherical, elliptical. So here we are saying that it is constant and it is spherical in nature. Then drag. So if you see, for drag, that is air in water, right? That means air is a dispersed phase. So air in water, the name only suggests that air is a dispersed phase. There you use the Schiller-Newman drag model. Okay. Now, if water and air is there, then again use the Schiller-Newman drag model. Okay. And air and water means if both the phases coexist, then use the segregated type of a model. Okay. So this is to account for the drag. Remember the drag, then drag is the force that is kind of giving the momentum exchange. Okay. Now virtual mass. So now virtual mass generally, see what happens is whenever one phase is moving relative to the other, there is one like an inertia force will be acting on the other. So that is taken into account by this virtual mass. So here one virtual mass coefficient of 0.5 constant coefficient type is being added. Okay, to this will account for the force due to the virtual mass. Now heat transfer. So if you have to simulate heat transfer, then we need to take, here in this case they have used the Rance-Marshall model for heat transfer. Similarly, if there is phase transfer that is happening, we do that. If there is lift that is being generated, we can add that. And then wall lubrication. What is wall lubrication? Generally, these bubbles, when they go closer to the wall, what happens is because of the small flow between the wall and the bubble that is there, there is a what I can say push that the bubble feels when it goes towards the wall, and that is modeled by the wall lubrication force. So if that is something that needs to be modeled, that is added. Turbulent dispersion, because of the motion of the bubbles, or some turbulence is generated, so that is taken into account by the turbulence dispersion. So now all these things are there. Now you say that why only Rance-Marshall, why only Schiller-Newman, why not something else? Okay, what are the other options that are available for me? If you want to know all of them, okay, somebody is talking about swarm factor. Swarm factor means if the bubbles are kind of accumulating, coming closer to each other, right? There is a group of bubbles. Then the drag on them may not be the same as these individual bubbles. So if there is swarming effect that is there, so that will change that. And for that, then swarm corrections have to be added. Now, I want to show you something. So what you can do is, if you want to know what are the various models that are available, the best way to do that is to go and look at the source code. As I told you, the one option is you just what you can say, make a naming mistake or something on one of the models, and OpenFOAM will say, okay, this is not the correct one. The correct ones are. That is one way to look at it. The other is, I will show you the other way. Okay, the other is you go to your installation directory. So, okay, that is computer. So our installation directory is in OPT. Remember OPT, where OpenFOAM is installed. You go to that, go to applications, solvers, and in that we are in multiphase. So go to the multiphase solvers. Okay, then we are using the multiphase Euler form. Remember, because we are doing two fluid model, Euler-and-Eulerian framework, we are using the multiphase Euler form. Now in that we have to go to interfacial models, because drag and all those things comes under interfacial models. So in that we see various drag models are there. So if you want to look at what are the drag models available, you can open them. Okay, there are n number of drag models that are available. Urgent, then Gidas for urgent venue, then Ishizuber is there, segregated, Tomiyama correlated, venue, all these things are there. Now, when which drag model will be used, for that you have to really look into the literature for all these models. Means you need to really go into this and see where they are applicable, what is their application range and all of that. Now if you open any drag model, you can look at the .c file. Okay, and you can, if you zoom in, you can see, look at what is the correlation that this Schiller-Newman is using. So Schiller-Newman drag models, the correlation is 24 into 1 plus 0.15 RE raised to the power 0.67. Okay, and that is something also you can search and you can verify. Okay, just let me see. Yeah, so here if you see, somebody has added an image. So it is 24 times 1 plus 0.15 RE raised to the power 0.687. That is what is being modeled over here. Okay, so that means you've understood this. So using this as a template, you can also modify, make your own drag model. Okay, you want to change something, you want to tune it for your specific case. That is something also that can be done. So this is regarding the drag model. Now, similarly, you can go ahead and you can look at various heat transfer models, various, what you can say, lift models, then swarm correction. Somebody was asking what, so swarm correction, there are again, there is one is no swarm, then swarm correction, Tomiyama. So different things are available. You can look into that. Okay. Apart from this, yes. So I think this much is sufficient for this. So that is what I wanted to point out. Now, for the next case, bubble column. Instead of bubble column, now we have fluidized bed. Now, fluidized bed is again a very important case, because if you look at it, let me go to the base file. That is something that I wanted to show. In this, because it is solid particles in air, the particles are always the dispersed phase. In air will never become the dispersed phase. So that is one thing. And here in this case, particle size will not change with pressure, or it will not change with temperature, whatever it is. So that's why the constant diameter model has been taken. Now over here, we have also specified something called as alpha max. This is the maximum packing fraction. That means even if the particles were to, what you can say, go down, and I will show you the case first so that you understand it better. I will run it once. Okay. Yes. So if you see, I start off, and if I look at alpha dot particles, right? If you see, all the particles are at the bottom. Okay. But if you see what is the maximum packing fraction, okay, the maximum fraction is not very large. It will not become one. Why is that happening? Because if we have spheres which are kept one on top of the other, even if they are kept, what you can say, completely packed, they will not occupy the complete volume. Right? If you must have seen that video where one professor is putting some balls into a what you can say, into a jar, then say, is the jar empty? No, you can add some little fine grains, you can add water that way. So the volume will not completely be occupied by these spherical balls. So that's why this is the maximum packing fraction, or this is the maximum alpha that can be achieved. Hmm. So this is one thing, and then we don't have any blending over here, right? Why blending is not there? Because in such a case, you always have particles to be the dispersed phase and air to be the continuous phase. That's why no blending is needed over here, as opposed to bubble column where that dynamics may change. Okay. The other thing that is important in this case is that here the properties. Yeah. Something momentum transport, right? Yeah. So here these properties, right? So even though the simulation type that is mentioned is RAS, this is not to calculate the turbulence, but this is to calculate the what I can say, viscosity and all those things. Because here it is based on these calculations are based on the kinetic theory for granular flows. So the how the what I can say solids will interact, what will be the viscosity and all those things, that is taken into account by the kinetic theory of granular flows. That is based on or built on the RAS framework. That's why it is coming over here. But that doesn't mean that this is a turbulence that is being added. So that is one more important thing. Now, I've said many things. You may forget all this, but I want to, what you can say, share a couple of resources that you can look into. Let me do multi-phase simulations. Two very important resources which I found very helpful while, sorry, open. Yeah. So one is this document by Wolf Dynamics, around 176 pages. They have discussed a lot of them, but not all these cases in details, right? But you can look at some of the, what you can say, they give, they sometimes, they tend to, mention why to use which value, in which condition you should use which value. So if you get time, you should go over this and read this and try to understand the interface compression that I was talking about, right? So in especially in what I can say bubble column and all, we don't need that. But this interface facial compression is there so that we want to have a sharp interface between the air and water. Because numerically what will happen is the interface will start to diffuse. So over here we add something called as a compression velocity to kind of what you can say undo that kind of a numerical diffusion, if I can say that. Okay, so this is one good thing. So here you see they have specified when to use two correctors, when to use three limiters, in which case. So they have given some very nice what you can say thumb rules. Again, this is not what I can say, if they have said use one only, you'll use one. No, this is just a thumb rule for you to take and then change based on your case, right? Specific case. This is one. And the other very important or very good document that I saw was of yes, this one. So this is a very good resource again. So this is done by Professor Norouzi from Iran, and he has maintained. Maybe there are only two tutorials in this case, three actually. Hmm? If you want to do some combustion modeling and also for that also they have. But where was that? Multi-phase. Let me go to multi-phase and then tutorials. Yeah. So they have a couple of good tutorials. So if you want more information on this, you see this is for a older version. This will work in V7 only because this is for two-phase Euler form. That is kind of now deprecated and we have multi-phase Euler form. So certain things may be different in this, but the general theory, whatever he has explained in this, given a very good write-up, so that will apply even for the multi-phase Euler form. So if you want to understand like what is this, what is kinetic theory of granular flows, he's not explained that, but what are the models that are available? He has given at least some general idea. So he's listed down the models. Like say I was talking about isothermal models. So the diameter is based on the diameter and pressure. Okay. So such things. So various models that are available. So at least this will get you up to speed. Remember this document also will not completely help you. It will just help you to what you can say, understand the basics, then you need to look into research papers, and Professor Naren suggested some good resources. Read them, then you will be able to, kind of do some very good simulations on this. So I think with this, I would like to now stop and then hand over to Manzil. So Manzil will now start and he will give a talk about dynamic meshing, why dynamic meshing is important, and some very good simulations have been done. So I hope that you are, you will like it. So I think I have answered most of those questions.